Good afternoon, and welcome to a cold and rainy Monday afternoon in business statistics, and we're talking about regression. So when the class first started, the first person that came in, I asked, how many people do you think will be in class today? And he made a prediction of how many folks he thought would show up. And do you remember what you predicted? Three people he predicted would show up. Okay, so that's what we do. We make predictions. You start with what you know about the world, which is how many people typically show up. And then you add some additional information, which is it's cold and it's rainy. And people don't like coming to class on cold, rainy days. So we think there might be fewer people than normal. And so we guessed 3. Now we could make a model out of that prediction. And the model would equal the prediction plus error. Okay, so if you guessed or predicted that 3 people would show up, and then we look at how many people are actually here, how much error is there? 1, because there's only 2 people in class. Now, the reason I stress that error is that gets really important. I'm going to talk about independence of errors as part of the lecture today. When we make a prediction, which is with the straight line, any dots that are not on that straight line in our scatter plot, those have a certain amount of error. If it's a really good prediction, like in this case, you're off by 1, well then that dot's going to be really close to the line. And if you were to guess a number where the dot was far from the line, that would be a guess with a lot of error in it. So what we like is a predictive model in which we have the least amount of error built into our prediction, which we can then use to make a prediction about something perhaps in the future. So not so bad taking our cold, rainy afternoon and turning it into a lecture about regression, or models and prediction. All right. I want to go through a little bit of math. And, you know, typically I'm just looking at the broad strokes, the more, you know, the philosophical part of the statistics, and let's understand the concepts. And I don't do a lot of math. But in this case, I want to show you using a very simple formula, or rather a very simple data set, just a little bit about how the math works and how we make the predictions. And the reason I want to do that is because I want to get to something about making predictions, and it makes a lot more sense if you see how we got there. So let me show you simple linear regression by hand and walk you through first the assumptions for regression. I've mentioned before, especially when we talked about ANOVA, even when we talked about t-tests, that all of the tests are built upon assumptions. And if the assumptions are incorrect, then the predictions or the outcome could be incorrect. So some things we need to know about regression. Number 1, the independent variable, or the predictor, that goes on the x-axis. We're going to use that to predict something else. With simple linear regression, we have 1 predictor and 1 outcome. Both that independent and dependent variable, both the predictor and the outcome, must be quantitative scale level variables, something that exists on a scale, 0 to 100, or maybe even a smaller scale, but it exists within that scale level of measurement. We should check both the independent and dependent variables, the predictor and the outcome, for outliers, make sure that we don't have extreme outliers. Not so much univariate outliers, but bivariate outliers. If it's an outlier for both the independent and dependent variable, that's where our problem might arise. So we want to check for outliers, and we want to check for normality. It's actually a normality in the distribution of the errors, and I'm going to show you how we would look for that. Independence of observations. So for instance, we use that height-weight example that we've used several times. Your height and weight is independent of the person sitting next to you. There's no relationship between those. The way that we actually test for this, however, is not with the measurements, but with the errors. So we want to look at the residual errors, the misses in our prediction, and then the errors should be independent. We can observe that. Linearity. If we're going to do linear regression, it helps if there is a linear relationship between the independent variable and the dependent variable, such that They exist on a straight line. They're not curvilinear, not a curved relationship between them. We're looking for that linear relationship. And of course, the stronger that relationship, the better that the x variable is going to predict the y variable. And then homoscedasticity, which is that the variance of the residual errors is the same across all values of the predictor. So imagine we have a straight line, and there are dots that are distributed around that line. The distance, the errors of those dots, should be pretty consistent all the way along that line. So if there was more variance on one end of that line than there was on the other, we might see something that looks like a cone. So we would see small errors, and we would see more errors as they were on one end of the scale versus the other end of the scale. So basically, we would look at the errors, the distribution of the errors in a scatter plot. We want to make sure that they're elliptical or round or cloud-shaped, not cone-shaped or funnel-shaped. Our hypothesis, we start with a null hypothesis. Well, in this case, our null hypothesis is really that we're predicting with the mean. The way that we would say that is the null hypothesis is that the slope of our regression equation equals 0, that it is a flat line. Because if it's a flat line, that means we're predicting the same number for everyone regardless of their x or predictor score. So our null hypothesis says that our regression model does not predict anything better than the mean, and we would be testing for that using an f-test or an ANOVA. Let's say f-test, which is an ANOVA. And then finally, we're going to set our alpha level of 0.05. That's typically what we use. We could set it to 0.01 or 0.001 or any other level, but for all of our examples, we'll use that 0.05 level of significance. So this is a regression for a straight line that we can turn into a regression equation. It's y hat, the hat means this is a predicted value, y hat, we're going to predict a plus bx. So we're going to take a constant, which is an a, and we're going to add to it the slope times a given x score. The way that we would approach this is to calculate b first using this formula. It's a rather complicated formula. I often say that it looks kind of dangerous, all those points and angles on it. It looks like something you could cut yourself on. So we're not actually going to use this. I'll show you what it looks like when we plug in some values to it. I just want you to know there's an equation that we could use to solve for b. Once we have b, we would then plug that into our equation. We've kind of back solved for a equals the mean of y minus b times the mean of x. We would solve then for a, so now we have a and b. We've solved for both of those values, and then we would plug those into a formula. So the way that we would begin this, we would start with our x and y values. We put this into Excel perhaps, and we would create a column for x squared. Having created a column for x squared, we would then multiply x times y, and we would create that column. With those, we'll say 4 columns, we can then add them up, so we'll get the sum of each of those columns, and then having the sum of x, we can divide that by n, we can get the mean of x and the mean of y. Those values are what plug into the equation. So that's what we would plug into that b equation that I showed you. We would take these values, plug them into our formula, solve for b, which in this case would be a 1.6. That's our b value. Great. Once we have that, remember it's y equals a plus bx. Well, we solved for b. Now we need to get a. How do we do that? We're just going to plug in the mean of x and the mean of y into a formula, and then we'll solve for a. So given our mean of y and our mean of x, plug those in, solve, and we get an a equal to a negative 1.5. So what I want you to take from this is there are formulas that we use to solve for a and b. This y a equals a plus bx is our blank model, our model for a straight line. These are our a and b values. Plug them in, now we have a regression equation. Okay, so even if you forget everything up to this point, if you know that we can create two values, we can solve for them using some math, and we can plug them into a formula, now you know what you really need to know, which is this. I'm going to have you solve for or make a prediction based upon a given x value. So we are using x to predict y. We could take this equation, y equals negative 1.5 plus 1.6x, and we could plug in an x value and solve for that. If you want to play along, you could get your calculator or your cell phone and type in some numbers. Here's how we would solve for this. If I asked you to predict for x equals 4, you would, first of all, multiply, so it would be 1.6 times 4. And then you would add a negative 1.5, which is the same as subtraction. So you would simply subtract 1.5, and you would get a value of 4.9. So if I ask you, I've selected a person at random, and I want you to tell me what their y score will be. In the same way that I started by saying, I'm going to select a guy at random from the US population, I want you to tell me how tall he's going to be. Well, in this case, I've selected someone, I've told you that their x score is 4, what do you predict their y score will be? You would guess 4.9, based upon this model. Well, what if we have an x value of 5? You would take 1.6 times 5 and subtract from that 1.5. You get a value of 6.5. One more prediction. If I ask you to predict for 7, same math, 1.6 times 7 minus 1.5 gives us a predicted value of 9.7. Now we know how you use a regression equation for prediction. Once you have created that regression equation, I could give you any particular x value. You could solve and make a prediction for what the y value should be. Okay, now let's see how you would do that using JASP. Now I'm not going to open up JASP. I'm just going to show you the settings. There is a video that I've already created that shows you how to do this. Now here we are using jobsatisfaction.sav. That's our data set. So let me mention, this is an SPSS data set. It's actually a smaller version of a data set that I used for my dissertation. So this SPSS data set would open beautifully if you have SPSS installed on your computer. Most people do not. But you can open it in JASP. And the way that you would do that is download jobsatisfaction.sav to your desktop, open up JASP, and then you could go to the main menu icon and then open computer, desktop, and on the desktop you would see this SAV file. It won't open in you won't open in Excel, it won't open in other software, but it will open in JASP if you follow the steps. But what it will not do is you can't just double click on this and expect it to open. You'd have to have SPSS installed for that to occur. But you can open it in JASP. Once you've done that, we can do this regression. I'll mention the data. This is 200 folks, 200 counselors in this case. We are going to predict their job satisfaction. How much do you like your job? And we're going to predict that from level of burnout. Now, hopefully the relationship between these two variables is intuitive. The more burned out that you are, the less you like your job. So we should see a negative relationship between these two. People who have high job satisfaction probably have low burnout, and people who have low job satisfaction have high burnout. So we could then predict your job satisfaction if we know your level of burnout. Now the way we would do this in JASP is you would, having opened up the data set, you could just go to the regression option and choose correlation, because the first thing we want to do is create a scatter plot. Just make sure there's a linear relationship between these two variables. And you would simply move the job satisfaction and burnout variables into the variables box. I clicked some of the settings for reporting significance. I just like to see some asterisks that tell me whether or not there's a significant relationship. Flagging significant correlations. And for the plots, I got a scatter plot with the densities and statistics. And that's what this would look like. So this is an example of what your output will look like. We do see a negative relationship. The job satisfaction, rather burnout, is on the x-axis, and job satisfaction is on the y-axis. And so when we see low levels of burnout, closer to 30, we see higher levels of job satisfaction. But now follow that x-axis to higher levels of burnout, around 60 and 70 and 80. Now we see lower levels of job satisfaction. So there is a pretty good linear relationship between these two variables. That's what we want. This is going to be a good regression equation, which we will do by going back to the regression option. It will create a new analysis for us. We'll choose linear regression. So we are trying to predict job satisfaction from burnout. So job satisfaction, the thing that we are predicting, the outcome, is going to go in the dependent variables box. And burnout is our predictor. We just have one in this example. That's going to go in the covariance box. Once we've moved those in, you'll start to see the results appear in the results window. A few other settings. Under model, we'll move the burnout into the model terms. Make sure we have the include intercept turned on. Just a real simple step. And then under statistics, let's get model fit. The R-squared change, descriptives, estimates should be on by default. And then collinearity diagnostics, that will allow us just to check for one of the assumptions built into the test. The R-squared change isn't going to tell us much right now, but we will use that for multiple regression because that's going to help us to compare models, the change in the R-squared. For residuals, we do want to check a few of the assumptions. So under the residuals, we get statistics and Durbin-Watson. And then for the plots option, we'll get residuals versus predicted. So this is going to tell us whether or not the residual errors are randomly distributed around the bean, essentially. And we'll get a QQ plot for standardized residuals. Having done all of that, we're going to see the results appearing in the results window. Let's walk through this output and make sure you know how to interpret it. The R for model 1 we see is a 0.65. I should have checked this when we did the scatter plot for the regression, or sorry, for the correlation. We would find the correlation between these two values is a 0.65. So when we only have one predictor and one outcome, the R value is going to be the same as the correlational coefficient. If we have multiple predictors, then that R is going to change from the correlation of any one of those predictors, because we have multiple correlations. Really, we'll have partial correlations we'll actually be dealing with. The R squared, of course, is the R value squared. Here's the interpretation for that. This is our coefficient of determination. 42.3% of the variability in job satisfaction is explained by burnout, which is actually a really good predictor. So we're explaining about 42% of how much you like your job just based on one particular score. And that gives us a pretty good model to work with. Now, the R-squared change, you'll see, is also 0.4226. That's the same as the R-squared because it hasn't changed. Or it's changed from nothing or just predicting with the mean. So those two are going to be the same. If we had multiple predictors, if we were building a model, we would see that R-squared change being different for each step of our model. I'm going to save the F change and degrees of freedom for the next bit of output. We'll look at the ANOVA for those two. I also want to point out the Durbin-Watson. This is autocorrelation. This is where we have the two variables that are so closely predictive, it's like they're predicting the same thing. They're so highly correlated. So the Durbin-Watson statistic is just a check that we use to make sure that the variables that we put into our model are not too strong. And this is going to be particularly important when we have multiple predictors. And in this case, the Durbin-Watson runs from 1 to 4. That's the range of the test. We want numbers around 2. So in this case, our statistic is a 2.07. That's really close to 2. So that's good. These data meet the assumption They're not too strongly correlated. So now we're going to look at the ANOVA output. What this f-test is telling us is whether our model predicts better than simply predicting with the mean, or better than nothing. That's what we're looking at. This first model with a predictor, almost always you will see this is statistically significant. If there's any kind of correlation between the x and the y, this model is going to be significant. However, when we start building models, we start adding multiple predictors, we're going to see that there will be some models that are statistically significant. If we had model 2, it was not significant. That means that adding a second predictor doesn't improve our model. It's not better than model 1. So here we have the statistical significance for the whole model, as we're comparing, and here we have degrees of freedom. There's 1 in 198. This would be like a typical f-test, a typical ANOVA. We have our f value of 144. Do you remember the value of an f-test when it's non-significant? Basically, the variation between and the variation within are the same. If you're multiplying anything by itself, it's going to be 1. And so if we have a non-significant f-test, the f value is going to be close to 1. In this case, it's 144. So this is, this is a big model. The probability, not surprising, less than 0.001. We could bump that out to a few more decimal places. We find it's a tiny little probability. Okay, so this tells us the model is significant. Adding burnout greatly improves our prediction of job satisfaction over simply predicting your job satisfaction based upon the average. So if I choose you at random from the people who are in this sample, and I say, what is your job satisfaction? If I know nothing else, I'll predict with the mean. But if I know your burnout score, I can predict much better. That's what the ANOVA is telling me. This is a much better model than just predicting with the mean. Here are the parameters for the model. We have standardized and unstandardized parameters, which is going to make a little more sense when we get into multiple regression. They simply come down to comparisons, and depending on what we're trying to compare. The unstandardized coefficients are always in the same units as the thing that we are measuring. So for instance, there's this job satisfaction scale that we're using has a range. We'll look at it again when we see the scatter plot. But there's a range of scores. Well, the unstandardized coefficient says that if we're predicting based on nothing else, we're going to predict that you have a job satisfaction score of 235 in this test. So that 235 is the same range, or is the same units as the actual test you took. Versus a standardized coefficient. If we have a standardized coefficient, it's like a z-score. And what that allows us to do is make comparisons within the model. Now, we just have the one predictor. But if we had 2 or 3 predictors, we could use our standardized coefficients to compare how well each of those are predicted. So we use standardized and unstandardized depending on which comparisons we want to make. Again, it's going to make a whole more sense once we have multiple predictors. With just one predictor, it's not nearly as useful. So here we see a t-value and a p-value. Basically, does adding this variable help the model? And then again, collinearity statistics. The tolerance and the VIF in this case are both 1. We're looking for tolerance values. Let's see, tolerance values should be above 0.1 and VIF value should be below 10. So when I started off, I said we solve for A and B. Well, here's where we get those scores. So how do you interpret these model parameters, and where do you get the values that we'd actually plug into that y equals a plus bx? Well, A is the unstandardized predictor for the intercept. That's our constant. It's our starting point. And then B is right below that. In this case, it's a negative 2.11. That is our B value. That's our slope. In this case, it's negative, because remember the relationship between burnout and job satisfaction was negative. So we will see it tilting downward. These we would plug into our equation. So now we have y equals 235.46 minus 2.11 times x. We will then be able to plug in any given x value, basically any burnout score, and I could predict your job satisfaction with this model. If I tell you that I've selected someone at random and this person has a burnout score of 25, you would take 2.11 times 25 and subtract that from 235.46. Again, it's a negative relationship, so as burnout increases, job satisfaction decreases, so we're going to see a lower number. In this case, we'd predict 182.71. We have 235 as our starting point. As your burnout goes up, your job satisfaction is going to go down. How about someone who has a burnout score of 50? So it's 50 times 2.11. You subtract that from 235, and we get 129.96. And we do the same procedure with a burnout score of 70, 87.76. Now this one, I'll tell you, this is a trick, but go ahead and do it. Go do the math on this one. If I tell you that someone has a burnout score of 120, we can still solve for this, and you get a score of negative 17.74. So what that's saying is this person has a job satisfaction of negative numbers. That seems kind of odd. I mean, it's one thing to have like no job satisfaction, but to have negative job satisfaction? So what happened here? Well, to answer that, we're going to have to look at our scatter plot and our predictions, which we're going to do here in a moment. But already you should be suspicious that something's wrong with this prediction, and we're going to figure out exactly what that problem is. So for instance, the value of the correlation. For the correlation, we go to the output, we find the R value, and the R value in this case is a 0.65. So to find the value of the correlation, we look for R. Second question, is the regression model, ANOVA, significant? Do you remember this? Do you remember the answer for this? Was that F value statistically significant? Oh yeah, that was a huge F value. So we have a model that it is better than predicting with a mean. And here's how you would write that up in APA style. So we would report, first of all, the correlation, which is in this case the B value. So we would report R equals 0.65, comma, and then our F with our 2 degrees of freedom, 1 and 198, equals 144.94. That's coming from the ANOVA output. And then finally, that's statistically significant, p less than 0.001. That's an example of what the write-up, the basic write-up, would look like. So what about the coefficients? What is the coefficient of determination? Well, that is the R squared value. So we go to our findings. That's a 0.423. Do you remember how we interpret an R squared? The first thing you should do is turn it into a percentage. So 0.423 becomes 42.3%, and that is the percent of variability in outcome that is predicted by variability in the predictor. Here's how that would look. 42.3% of the variability in job satisfaction, or outcome, is due to variability in burnout. Now, when I say it like that, you might say, that's starting to sound a little bit causal, because when I say variability in job satisfaction is due to burnout, it's like I'm saying burnout causes low job satisfaction, which is an easy assumption to make. But again, this is correlation data. So because correlation does not imply causation, all we can really say is that burnout is associated with low job satisfaction, not that burnout is causing low job satisfaction. So when I say is due to burnout, that may not be the best way to phrase that. Now, if we did multiple, we could do other examples and experiments, and we might be able to demonstrate some kind of causal link. And there certainly is an intuitive causal link. But I just want you to be reminded that we have to be careful the way that we phrase the wording that we use around this type of regression. The value of the coefficients for A is your constant. So it's going to be the 235.46. And B is the unstandardized coefficient for the first predictor, which in this case was a negative 2.11. And here's that question that we left on when I said, there's something suspicious about this prediction. Which of those four predictions was most speculative? Well, let's take a look at the scatter plot and see. I ask you to predict using values of 25, 50, 70, and 120. What I'd like you to do is look at the range of the predictors on the x-axis. What is the lowest value on the x-axis? It's a 30. And the highest value? Well, the highest value on the x-axis itself is an 80, but the highest actual score is what? Somewhere in the low 70s. Okay. So when I ask you to predict with 120, think about the range of the x-axis. What is the problem with using 120? It is predicting outside of the range. Our x values, our predictors, only go from, we'll say, roughly 30 to 80. Meaning predicting outside of that range is going to become highly speculative. And in this case, it gave us a negative value, which just doesn't make sense. The lowest value you could get for the job satisfaction scale, just because of the way the scale is designed, might be something like 30. So it's predicting a value that isn't even possible for you to get on this particular measure of job satisfaction. That's the problem with predicting outside of the range. And so the final thing that I want to leave you with is an example of the APA linear regression write-up, which, as you can see, would be a whole lot more. I don't expect you to write this all down here, but I do have this in the notes for this week, so you can see what that looks like. But this gives us an example of how we might write up a simple regression equation. So all of that's simple regression. When we talk about multiple regression, or hierarchical regression, or model building, it gets much more complex. So I always tell my statistics students that, because I know that stats is difficult, but all of the stuff that we're learning right now, we're still kind of on the lower slopes of statistics. There is so much more to know, so much more complexity built into these models, which is why if you get good at statistics, you'll always have a place, whether it's in academia or in business or just having friends that are doing research, people will want to pull upon your expertise if you know some statistics, if you understand a little bit about the complexity of these models. All right. Well, that is everything that I wanted to tell you about for this week. Do you have any questions before we wrap up? All right. Well, thank you for being here. Thank both of you for being here. I'm so glad you made it on a cold and rainy Monday afternoon. Hopefully we'll have better weather next week, and I'll see you then.